So we start with a whole case first. Okay, let's go. Okay, quite good. What is the opposite word of adaptive immune system?
Innate immune system.
Innate immune system, right? Innate is a 선천, adaptive is a 후천. Recall. Okay, move on. Okay, B cell and T cells, they are the definitely adaptive immune system. Dendritic cell is an antigen presenting cell. So that is also related to specific targeting. Innate immune system is just attacking not selectively, not molecular level. It's just attacking in general. And adaptive system is a molecular level specificity they have. So that's the main difference. What is APC?
Antigen presenting cell.
Antigen presenting cell. Okay. If you have any other enemies, the cells swallow the cell, and then break it down, and then present small part of that foreign body onto the cell surface. That's the antigen. Antigen presenting cell. Dendritic cell is a representative antigen presenting cell. Macrophage is also, they can swallow the phagocyte, but they can also present those antigen. B cell, they do present antigen too. And then it can be activated by the other cells, like T helper cells. T cell does not have antigen presenting the function. Okay, very good. CD4 cell is a T helper cell. And what is a T killer cell?
CD8.
That's a CD8. Okay, CD8 is a T killer. CD4 is a T helper. And this T helper cell is a target of HIV, the AIDS, the virus. AIDS virus attack this CD4, and T helper cell does not have proper function, and we have an immune problem. That's why it's called as an adaptive immune syndrome. Okay, cancer immune syndrome. Okay, very good. CD8 receptor is the make complex with the MHC1. And how about the MHC2? MHC2 binds to what?
CD4.
MHC2 binds to CD4. Okay, that's the other partner. TCL is a T-cell receptor. This is a single chain FV. Not bad. T killer cell is utilizing granzyme. Granzyme is a protein breaking down enzyme, protease. And T killer cell also use the weapon. Do you know the name?
Perforin.
Perforin. Perforin is another the T killers, the weapon. What is the function of the perforin?
Make a hole in the tumor cell.
Make a hole onto the target cells. Okay. Perforin make a hole. Granzyme enter the cells, and then they break down the proteins of the target cells. Okay, those two are main weapons of T killer cells. Okay. PD is expressed on which cell? PD1 is expressed on
T cell.
T cell. On the T cell, PD1. On cancer cell, PDL1, PD ligand 1. CD4 is on T helper cell. CD8 is on T killer cell. Right? Okay. Okay, very good. So if you use your own cell, that means the genetic background is the same. That's what we call autologous. If you use somebody else's, then we call allogeneic. And the others are just the random adoptions. Okay, perfect. Chimeric antigen receptor T cells. Okay. T cell receptor is a TCL. TCL is a T cell receptor. My question was, TCL is replaced with what? Right? So originally, T cell has a T cell receptor. It's like a combinatorially made antibody-like structure. It's a combinatorial receptor. And this one is similar to antibody, but different from antibody. So in principle, you can change TCR with the antibody. The antibody has 4 fragments, so it's difficult to express all 4. together. That's why single chain connected to one fragment. This one is a popular mimicking molecule of antibody. So this molecule is usually used to replace this TCL. Okay, today's you guys studied quite okay, much better than last week. Okay, let's move on. Okay, today we start with this immune cells. You already have seen have studied those different types of immune cells from the video clip, but here are some more. So originally we had stem cell, and among those stem cells, if the adult stem cells, which is making blood cells, those stem cells we call hematopoietic stem cell. This is a precursor of all kind of cells, okay, all kind of blood cells. Blood cells, they can be divided into two categories. One is a lymphocyte, and the other is myelocyte. So one lymphocyte class and also myelocyte. Lymphocyte, they have T cells and B cells. When B cells are fully differentiated, and when they started to make antibody, specifically we call plasma cells. So plasma cell is a matured B cells. Okay, so these are from the same ancestor, and these two cells, B cells and T cells, they are responsible for adaptive immune system. All other cells here, they are mainly for innate immune systems. So interestingly, very similar to T cells, but there are so-called NK cells, natural killer cells. Natural killer cells, they do not recognize a specific antigen. They just recognize whether the cell is self or foreign. Okay, so this is kind of a little exception from this lymphocyte, but this is the innate. And then among this myelocyte, and one of those representative one is macrophage. Macrophage, when they are circulating in the blood, they are called as a monocyte. Monocyte means the nucleus is a single nucleus. In comparison, other type of cells, much bigger cells here, these cells, they have a lot of granule inside. That's why these cells is called as a granulocyte. And these granulocytes, the nucleus morphology do not look like just a single, looks like it's a multiple nucleus. So this is one class, and then this is another class. So this is a monocyte differentiate into macrophages. So usually we have the image of a macrophage like an amoeba-like. So once this globular monocyte, they differentiate and they become this kind of a macrophages. Okay. Now, funny thing here in granulocyte, they are divided into three classes. Now, if you look at those names, neutrophil, eosinophil, and basophil. Eosino means this is acidic. Baso means this is basic. Okay, neutral means this is neutral. So the name was given by different dyes: acidic dye, basic dye, and no dye. Okay, so when the scientists, the blood scientists, when they added red color of acidic dye, some populations were stained as red color, and they called these cells as eosinophil, acid-like cells. When the purple color of a basic dye stains, these cells is called basophil. This means base-like cells. Neutrophils are not stained. That's why they are called as a neutrophil. That's quite funny, right? So it's similar to gram-positive and gram-negative situation. In the beginning, without any molecular evidence or the reasoning, they just used those names based on stained the dyes. If the dye stains gram-positive, dye do not stains, then it's a gram-negative. Similar the type, but a little differently. Acid staining, eosinophil. Base staining, basophil. No staining, neutrophil. Okay. So anyway, in our the blood, neutrophil is the most abundant cells. And these cells, once there's any problem, they secrete a lot of these granules. Those granules contains chemical weapons and biological weapons. Okay. That's why these cells are kind of first line of the defense, and they are not specific to the antigen. They attack all kinds of invaders. It can be virus, it can be bacteria, or even it can be maybe cancer cells or transplanted somebody else's cells. Okay, so this is the two big classes. Oh, another important one, erythrocyte. Erythrocyte is a red blood cells. Number-wise, this one is occupying more than 99%. Altogether, these white blood cells, they should be less than 1%, approximately 0.1%. Okay, relatively very small number. Once the number of this, the white blood cell becomes bigger than, let's say, 10%, then we call the disease as a leukemia. Okay? Leukemia's leuko means white. Okay, so this is overview of blood cells. Now, in terms of functions, only B cells and T cells, this is lymphocytes, and also natural killer cell, this is lymphocyte. These cells are adaptive immune system cells, and they recognize a specific antigen. And then this side, all together, these cells do not recognize antigens. So that means this is more primitive system. This is a more sophisticated system, right? B cells, they make antibody. T cells, they have an antibody-like structure, so-called T-cell receptor. They are not same, but their principle is quite similar. Okay. Now CD, you have heard the CD4, CD8. What is a CD? Anybody knows? Nobody knows?
Cluster of differentiation.
Say again.
Cluster of differentiation.
Sajin said a cluster of differentiation. What is it?
Kind of specific protein on cell surface.
Okay. Every type of our cells in our body, they are differentiated from stem cells. And then out of 30,000 of different protein sets, they start to express some specific set of proteins. And some of them is expressed on the cell surface. Okay. So sometimes some protein is show up, or some proteins are disappear, depending on those differentiation stages. That's why some cells, if you have some specific cell, there may be different set of proteins. If you look at those markers, then you can define what type of the cell is that. Those kind of representative the biomarker proteins, majority of them are protein, but some of them are carbohydrates, but some of them are lipid molecule too. These molecules is called as a cluster of differentiation. Or sometimes it is called as a cluster of designation. Then, out of 30,000 different proteins in our body, how many CD do we have, you think? How many CD has been discovered so far? It's just a guessing. You can try. You heard the CD4, CD8, and CD19. Okay. Have you heard bigger than CD100?
CD 137.
37, 137, yes. There may be something like that. Have you heard of something bigger than 200? I asked you whether how many CDs are discovered. Actually, that's not the proper description. CD is not discovered. Of course, it's discovered, but CD is just designated. We just gave it the name. This protein can be useful to distinguish different cells. So that means if there are any protein always expressed on cell surface, then those protein may not be good candidate of CD because every cell has it and it does not show any discrimination. Right? So some markers shows up only in specific cells, not in other cells, and those are good candidates of CDs. So these CD sets are fundamental set for discriminating different type of cells. So once we define this CD, they develop antibody for CD. So that means anti-CD. So utilizing those antibodies, they can discriminate the different type of cells. Okay. Every year they redefine of these CDs, and also good batch versus a bad batch. Even though same CD, same protein, still the antibody can be different, right? So that's why they collect those informations and update every year. Last year, the total CD number for human being was 371. 371. Among animal models, the best studied animal model is mouse, not rat. Okay. For mouse, we also have about 350 the CD systems. So utilizing those 350 or 370 CDs, based on those antibody system, we discriminate different type of cells. Okay. So then you may not be surprised to hear the CD 250 or CD 301, something like that. Now, next one is the APC, antigen presenting cell. When any foreign body is swallowed by the cells, they break it up and then they represent, showing off some fragment of that the foreign body to the outside. This type of cells we call antigen presenting cell, APC. Dendritic cell is one of those representative one, and macrophages and B cells. B cells, they need to interact together with the other type of cells. That's why they have an antibody, and also they have this kind of antigen presenting. Now, this antigen, the fragment, it can be very small. If it's very small, then it's difficult to show off. That's why you need to have some helper protein, holder protein. This holder protein is called as a MHC. Okay, MHC is major histocompatibility complex. Histo means histo is a tissue. Okay, so compatibility is whether we can accept it or not. So this is an important molecule for transplant of organs. So that means this MHC, there are big class-wise MHC1 and MHC2. And interestingly, MHC, for different people, the number of MHC kinds is not as many as of the antibody. So that means it's not millions. But MHC also 20, 30, 40 different MHC. And we have MHC1 and MHC2. Everybody has different MHCs. Sometimes it can be same by chance, but it's difficult to match both of the MHC1 and MHC2. Both of them are same is quite difficult. That's why when we do the organ transplantations, like a kidney transplantation, usually they check whether the donor and acceptor are matching or not. They look at the structure of an MHC. If the MHC is similar or same, then organ transplantation has much better chance. So that means I have my own MHC, and Youngwon has a Youngwon's MHC. That's why if Youngwon's tissue or the cells come into my body, then my defense system, the specific example is NK cells, natural killer cells. They recognize the MHC. If it's my MHC, they don't attack. If that is a different MHC, then they start to attack those cells. Okay, natural killer cells. We said that's not adaptive immune system. That's innate immune system. But at least they recognize whether this cell is my cell or somebody else's cell. It's kind of an intermediate, right? So MHC is checking. Then if it's recognized, then if they have MHC, then they do not attack. If the MHC, there is no MHC or different MHC, then they start to attack. Okay. So this is APC. Now, MHC is representing antigen. And then when T-cell receptor bind here, there's another alpha protein should bind together. So this is a T-cell receptor. And then this is MHC. And then this is the antigen, small fragment of antigen. And this T-cell, if they bind to this cell, at the same time, they need to check CD8 is recognizing this MHC class 1. CD4 cells, they recognize this MHC class 2. Then they recognize two things. They recognize this antigen, and also they recognize, okay, you are one of us. You are my cells. This is a T cell, T killer cell, CD8. This is a T helper cell. They recognize this antigen, but at the same time, they recognize this is our cells, our helpers. That's why I do not attack this. If they recognize this, and if they recognize this is not my MHC, then they may attack these cells. Okay, so this kind of system is immune cells checkpoint. Immune cells' function is to attack foreign enemies, but at the same time, they should not attack our own cells, right? So that is happening through this kind of systems. Now here, so-called the immune checkpoint, PD system is occurring up. Not only for those antigen recognition part. Here's a T cell. Now I recognize you. Seems like there is the antigen here. So this antigen is expressed by tumor cell. Now whether I should attack this or not, that decision is made by PD1. PD1 is a switch off the functions. So PD1 is activated, then they stop. PD1 is the operating, then they stop immune system. That's why they do not attack the cells. So that trick was achieved by tumor cells. So tumor cell expressed PD-L1, ligand 1. So they bind here and activate PD-1 system. This activation is a switch off for the T cell functions. That's why T cell does not attack the tumor cells, even though they recognize this antigen part. Tumor cells, they can generate mutated protein or maybe overexpressed some proteins. Then they should be recognized by immune cells and they should be attacked. Then we can wipe out. But in this case, if tumor cell representing this one won't attack me, okay? This is common strategy by tumor cell. That's why in this case, if you add some other antibody, either binding to the PD-1 or binding to the PD-L1, either side is fine. Anyway, if they do not recognize it to each other, then this T cell is keeping the activity and they start to kill the target cells, the tumor cells. Okay, so this is the so-called immune checkpoint activation. Originally, that immune checkpoint was suppressed by tumor cells, but that one is released. Now this T cell is activated and they can attack this. Utilizing antibodies is similar to antibody drugs we managed last week, right? But the strategy is different. Last week, the antibody was binding to tumor cells' signal transduction pathways. It's similar to small molecule drugs, attacking those overexpressed kinase or signaling molecules. In this case, these antibodies, they bind to the molecule on immune cells, and activating those immune cells. That's how they work to attack tumor cells. That's why this kind of the drug we call immunotherapy for cancers or immune checkpoint drugs. Okay. Now let's see some of your questions. Now we start to look at the CAR T cells. What do you think? What is the difference between the CAR T and general T cells? Okay, let's look at a little more questions and let's think together. CD8 cells is a helper cells. CD4 is a helper cells. CD8 is a killer cells. They have a partner of MHC 1 and 2. So this is 1, this is a 2. And then there is some given protein name like CTLA4 and B7 or PD1 or PDL1. There are different kinds of immune checkpoint. And there may be many of them that I wonder other proteins, the functions or what. So in a sense, we are very early stage, at the very early stage of this discovery. So far we found, let's say, PD1 system and CTLA4 system. Of course, there are several more, but still the numbers are increasing. Which checkpoint is the most important? It's still we are testing them. That's why we don't know which one is the best one or better one for the selectivity or for the activity. If we activate the T cells function too much, that's also dangerous. Then they may start to attack our body. So that's kind of the autoimmune disease we should see. That's why we do not know all the function of all the transmembrane proteins so far. Even we didn't discover them all yet. Still, we are in the process of discovering those. And Sajin tried to give very good answers for this, but that's kind of a little more physical way how to separate those T cells. Can you give any other simple answer for this? How can you separate the T cells from blood? In the blood, we have T cells, B cells, macrophages, and granulocyte, and many different types of cells, right? How can you separate only T cells? Sajin's answer was by utilizing those physical difference of different other cells, we can fractionate to some extent. But let's just say T cell and B cell, they are very similar to each other. Size and shape is very similar to each other. So it's almost impossible to separate them by physical properties. Then how can you separate those T cells? The hint is you can use antibody.
Or Western blot.
Western blot means you isolate out the protein and then run chromatography, and your protein is bound to the membrane, and then you add antibody and you detect those proteins. Okay, to isolate the dongwu from your classmates, we grind up dongwu, run the gel, and we detect dongwu's specific protein. Maybe possible, but dongwu is already not alive anymore, right? So question is, if you wanted to isolate intact live T cells, how can you do it? Blotting, all kinds of blotting, southern blotting, northern blotting, western blotting, those are all utilizing cell extract. after breaking up the cells, and then run those protein or DNA, RNA as a molecule after the whole cells. So here is the technique so-called flow cytometry is invented. So the name of flow cytometry, cyto means the cells, meter means the measurement, utilizing flow system. Okay, so if you take blood, then you can flow those cells through thin tubes, and blood cells are the pass through this line, and then you give light source on one side. It's a 90-degree the irradiation. Then blood cell goes in, and then once this light touch this part, then they start to scatter. And this scattering can give, on this direction, this is a forward scattering. And this is this direction that can give side scattering or backward scattering. So two scattering information can be obtained. Then among these all different type of cells, so they have a different size and different granule amount and different contents. So different physical properties here. So if you flow these cells one by one, then these cells can generate forward scattering signal and side scattering signal. You can read very quickly, and then you can plot. So forward scattering, some of them is small, some of them are big. Again, here side scattering, small, big, and this is the count number. How many cells are counted here? Okay, like a histogram accumulated. If you plot this together, you can see like this. This is a forward scattering. This is a side scattering. Okay. Now you can see three big populations are generated by this system. This is our blood. This one, red blood cell is pre-removed by breaking down the red blood cell. Red blood cell is more than 99% cells. If you plot them together, majority of them is red blood cell. It's very difficult to see. So you remove red blood cell first, and then white blood cells. Now among these, all the scattering can give you the information about the size of the cells. It's a bigger signal, then that means that these cells are bigger cells. If this is here, this is smaller cells. Side scattering information, it gives information about inside the material of the cells. If there are more granules inside, they have bigger signal from side scattering. Okay. Scattering, but forward scattering is determined by its size of the cell. Side scattering is determined by those small vesicles inside the cells. Okay, so based on this, we can say this is a lymphocyte. This is T cells and B cells. This is a monocyte. Once they go into the tissue, then they become macrophages. And this is granulocyte. At least 3 different populations you can get very quickly. If you go to the hospital and if they take your blood, in 10 minutes they can tell you how many count of your red blood cell, how many count of your white blood cells, utilizing this technique, so-called flow cytometry technique. Here, lymphocyte, monocyte, and granulocyte. Very quickly you can get. This information is based on only for the scattering. But if this molecule is labeled with a fluorescent molecule, let's say, if you use the antibody, and that antibody is labeled with a green color, then when it passes through, when this is excited, not only scattering information, still you can get all the scattering, side scattering information. At the same time, you could get this green signal. Let's look at it one more time. These green cells can give the information of this green signal here. Okay. Now, if that antibody is labeled with the red color, now it can give you the red color signal here. Or maybe different color, let's just say green color, yellow color, red color. Now you can get different informations of the cells. Now, if you label CD4 antibody with a green color, CD8 antibody with yellow color, and CD19 with the red color or yellow color, then you can discriminate different kind of cells by antibody signals. This kind of antibody and also fluorescently activated one is called as a FACS. FACS is a fluorescence activated cell sorter. This is kind of a flow cytometry, but which is further facilitated by these fluorescence signals. Now you can count how many CD4 cells, how many CD8 the cells, not only for the counting, even you can utilize these signals. Once those signals, no signal goes here. If it's green signal, you can change those the voltage. Then you can collect green cells, or you can collect red cells in opposite side. Physically, you can isolate those cells. So now you can you can give the answer for my questions. How can you isolate T cells? Utilizing this kind of FACS machine. Scattering itself is difficult to use, but once you have fluorescently labeled the antibody, then you can use either CD4 or CD8, or common antibody for T cells are CD3. So if you use the CD3 cells labeled with the green color, then you can sort out those cells by fluorescence colors. Okay. So this technique is called as flow cytometry, especially they use the fluorescence. That's why this is called as fluorescence activated cell sorter. Okay. Utilizing this FACS machine, and you can isolate those cells. Now let's see. When T cell is developed in the beginning, they do not have CD4, they do not have CD8. These are double negative cells. Later, they start to express both CD4 and CD8, double positive cells. And later, they go into the either CD4 cell or CD8 cell. This maturation is happening in thymus. Thymus is a 흉선 in Korean. 흉 is a 가슴. Okay, 흉선, they mature into different cells. Now you can use anti-CD8 with a green color, anti-CD4 with a red color. Okay, and then you add this antibody to the mixture cells over here, and you label them. Then as you can expect, they can see like this: double positive, CD4, CD8, double negative. Okay. If you do not add any of this antibody, most of those cells are here. Now, if you add anti-CD8 is a green color, so this is a green channel. This is a red channel. Okay. Then you can see some populations are going up to this side. These cells are CD8 cells. CD4 signal with a red color, then you can see these cells are CD4 cells. If you combine them together, now you can see majority of them is double positive cells. This is immature cells. And then now this is CD4 cells. This is the CD8 cells. This is double negative cells. Okay. Utilizing this FACS machine, now you can tell how many percent. 69% of cells are still immature cells. Now, maturation of those T cells and B cells we mentioned before. So in the beginning, they start with a negative screening. If the cells do not bind anything, then they die out. That's the negative screening. Because they do not have any the specific binding the ability, then they go to apoptosis. Next step is they recognize very weak binding to our own body material. Then that's a positive staining, positive selection. They survive, only weak binders. And then, so in the beginning, if they don't bind anything, they die out. That means survived cells, they have a weak binding. Right? Next step is they check whether they strongly bind to our body or not. If they do, they should die too. Because if they strongly bind to our own other material, then they will kill our own cells. So 2 steps of selection is happening. And that is kind of amount issues, not absolute yes or no. If that weak binding is slightly increased or decreased, then those cells has a potential to attack ourselves or not, depending on how much of those activation of our immune systems. Okay, so in cancer, if there's an antigen is generated, if it's a very small amount, then even though there is immune response is happening, that's not strong enough. That's why the cancer cannot be removed. In that case, we help the immune system by adding vaccine. Then vaccine stimulate those response. And even though the same target was already there, still this extra vaccine can activate further of our immune system. Then they can start to attack cancer cells. Okay. So anyway, this is the flow cytometry technique. One very important application of this flow cytometry is measuring cell cycle. So we have studied this cell cycle. When the cells are entering this G1, now this is a resting state of cells. And then when they are ready to divide, they enter G1. Then they increase their cell size. And then once they pass this checkpoint, they start to synthesize DNA. So this is a synthesis of DNA S phase. And another gap here to prepare for cell division. And then mitosis happens here. During this cell cycle, most dramatic changes are DNA amount. Here in G1, G0, and G1, what is the amount of DNA? Amount of DNA, how do you define? Haploid, diploid, and if it's the sperm or the egg cells, if it's somatic cells, how much of the DNA do we have?
Diploid.
Diploid is 2N, right? So in the beginning, those cells in G0 and G1 state, those cell amount, the DNA contents is about 2N. And then it is increasing during those S phase because DNA synthesis is ongoing. At the end of S phase, now synthesis is done. Now the amount of DNA becomes 4N. And before and during those G2 and before those M, they stay as the 4N, double amount. When they divide, they come back to this 2N, then continue and they recycle like this. So to measure this DNA amount, usually we use this kind of a DNA intercalating reagent. This is one of those popular one, propidium iodide. This one is inserted into DNA structure. And once they bind to DNA, they become very strong red color of fluorescence they generate. Then utilizing fax machine, we can get this kind of information. Now here, this is a PI intensity. That means this x-axis is a DNA amount. Okay, and this one is a cell number. So by looking at this is a 2N. This is a 4N. Then by analyze this, so we can say this one is G0, G1. This is the S phase. This is a G2M, you can say. Even though actively dividing cells, usually they have this kind of distributions. That means 60–70% of cells, they are preparing in G1. And DNA synthesis is ongoing about 20%. And mitosis is about 10%. That means they don't want it to be in the vulnerable status, soft status. During those DNA synthesis, the cells are kind of unprotected. It's an open DNA structure, and DNA is being synthesized. This is kind of a vulnerable state. They don't want it to stay here long. After DNA is synthesized, they want to divide as soon as possible. Then they go back to this. Okay. And if there's any cells which goes into apoptosis, then cells are becoming smaller and fragmented. Then they look like DNA contents looks like less than 2n status. They can be shown here. This is the normal status of the cells. Now we can tell this is G0, G2M, this is S phase, and this is some apoptosis. Okay. So this is very common application of a flow cytometer. And if you look at the real data, they look like this. So majority of them is in G1. Small populations are in the apoptosis. And then some populations are accumulated in G2M and S phase. So this is kind of a healthy distribution of cell cycles. Now here, if you add any drug compound, let's say this is a normal, and if you add DNA synthesis inhibitor, then they cannot move into the DNA synthesis step. These cells are going to accumulate here. These cells are come back here, and then they do not enter this S phase. Now, these cells are arrested at G1 status. Then, by looking at this, what kind of a drug was used?
checkpoint inhibitor.
There are two checkpoints. Checkpoint was in cell cycle. One checkpoint was a G1S checkpoint. The other checkpoint is a G2M checkpoint. Okay, cell cycle also has a two checkpoint. And by looking at this one is which checkpoint was blocked?
G2M checkpoint.
This is the G2M checkpoint was blocked. So it can be either the checkpoint kinase was inhibited, or this one is mitosis is blocked. What was the inhibitor for mitosis? You have learned?
Microtubule inhibitor.
Microtubule inhibitor that is interfering those cell division. There are two kinds. One is overstabilizing those microtubule. The other one is interfering disassemble of the microtubule. Two kinds. Overstabilizing drug, do you remember? Very famous drug,
Taxol.
isolated from Jew tree,
Taxol.
Taxol. Taxol is overstabilizing. The microtubules should be dynamic. One side should be growing, the other side should be shortening. It should be in dynamic status to make a cell division. But overstabilizing is also block those cell division. Which one was destabilizing microtubule? That drug can make a seedless the melon. Seedless melon was made by Dr. Woo Jang-chun. Compound was a colchicine. Colchicine was blocking the here. So anyway, by looking at this cell cycle arrest, we can tell this is DNA synthesis is blocked. This one is mitosis or the checkpoint 2 is blocked. Okay. So this is what we call cell cycle or the status checking by flow cytometry. Here, what is the x-axis? X-axis is DNA content, DNA amount. Okay. Now, this technique can be used for many different kinds of applications. So another application is into the apoptosis. Apoptosis is a programmed cell death. When the cells are healthy, phosphatide setting is only facing inside. The first step of apoptosis, this membrane asymmetry is broken, and some of this phosphatide setting is exposed to the outside. Later stage, now the membrane is damaged and they make a hole. first stage of this membrane asymmetry broken, this one can be measured by protein so-called Annexin V. Annexin V can be labeled with a green color. And this is like an antibody, you can think. It's not antibody, but phosphatidylserine binding protein. And you can label with a green color. And propydium iodide. This was a DNA dye, just as we just seen just now. But this propydium iodide cannot penetrate the cell membrane. It can go inside the cell and stain DNA only when the membrane is damaged. Okay, so early apoptosis and late apoptosis. Now here, this is red color. This is PI signal, propydium iodide signal. This is Annexin V signal. Okay, now this population is a healthy one. This population, these cells do not have green signal, do not have red signal. Now, if you look at here, 1, 2, 3, 4, 1, 2, 3, 4. Early stage of apoptosis here. Which area do you expect to see the cells? This is a green signal. This is a red signal.
2.
You may expect new population is coming up here. This is early apoptosis cell stage. If it becomes late apoptosis, where do you expect to see new cells?
Top right.
1, 2, 3, 4.
3.
You can expect to see late apoptosis cells. If you see some cells here, that would be quite strange. It bypasses the early stage and just jump into the late stage directly, right? So it's a strange population. If you see something here, then your experiment is wrong. Something is wrong. So healthy cells slowly moving to early apoptosis, and then some population here, they move to late apoptosis. So utilizing this kind of systems, you can analyze whether these cells are healthy or not, and whether they are. If you don't see anything here, all the cell populations directly move here. So that means the cells are going into another type of cell death, not apoptosis. Then what is the cell death? Abrupt cell death?
Necrosis.
Necrosis.
It's a necrosis. Then you can tell whether the cells are dying through apoptosis or necrosis. Okay. So real data looks like this. This is healthy cells. Majority of them are healthy cells here. Small amount of dead cells, but this is common. And now some populations are in apoptotic area, and big populations are here. They are in necrosis of the area or late apoptosis rate. So this is the technique so-called the FACS or flow cytometry. Utilizing this system and combined together with the different antibodies like a CD4, CD8, or CD19, then you can discriminate different cell populations. So right now we are just looking at the two-dimensional data, red and green. Of course, you can plot this multidimensional. Multidimensional is difficult to show, but at least you can choose two the axes, and then you can see 3, 4, 5 different antibodies, positive or negative pattern. Okay, so this is a flow cytometry. Now some questions given by you. What do you think? Already we covered this topic. Anybody can make a comment for this? In this problem, what can be vaccine? What can be cancer vaccine?
Tumor-specific protein.
So some protein which is specifically generated by tumor. Then immune system is healthy, then we can eliminate the tumor by ourselves. Now, why do we need a vaccine?
to establish the memory cells.
Okay, memory cell can be a little different story. If it's the first time to generate. Maybe the tumor cells presenting those specific the protein is not high number enough. That's why our immune system, we see those emergence cases and then show those immune response if it's a 10%. But tumor express only the protein 5%. Then our immune system is not active enough to attack the cancer. That's one possibility. Or maybe the cancer cells presenting those tumor, the antigen, which is partially maybe blocked by other motif around. That's why it is not generating the immune response strong enough. Then in the case, we can give higher number of that antigen and then boosting our immune system from 5% to 20%. Then 20% immune system is strong enough to attack the cancer. That's one possibility. Or maybe cancer cell presenting part is partially hidden. So we give the exposed the antigen and then activate the T cells and B cells. And then they generate enough the weapons, then they can attack. That's another possibility. Now, memory cell or not is a different story. If the immune response is not strong enough, then anyway, the memory cell does not work either. So this is kind of a balancing, maybe boosting our immune system in general. That's one approach. Well, another approach is specifically expose those immune system to that the specific the antigen more strongly. So two approaches is possible. So here, if you lose those balance, if you activate our immune system too much, then now we are in trouble. That activated the immune system can attack our own cells because this tumor or the antigen, if it's not a mutated one, if it's just a number issue, let's just say, tumor has 10 copies, normal cell has 5 copies. And our immune system, the best situation is in between. But if it goes too strong, then it can start to attack normal cells. Okay, so that's why we need to get the balance of too strong versus too weak the immune system. What do you think? This was a Thomas question.
Yes.
Now, can you give some answer for that?
Okay. Well, for a universal vaccine to be developed, there should be some protein that should be expressed on all types of cancer. But I don't know if that protein can be discovered. So if that protein is discovered, I think there'll be a chance.
Okay, so as Thomas said, the ideal case is all the tumor has very common antigen. If we can find it, then that would be really ideal. We can cure them all, but it may be very difficult to expect because tumor is quite heterogeneous. Even the one person's tumor, they keep changing. So different parts of those tumors, old one versus a new one, or metastasis, the one. Each of them can be different. So that's why finding out a very common one vaccine would be quite difficult. So our best choice is trying to find some vaccines which can cover as many as possible the tumor kinds, but actually it's quite challenging. Another approach can be if you wanted to activate almost everything, then it's just boosting the immune system itself. So usually it helps. The problem is if it goes too much, then we may suffer from autoimmune disease. Okay. This is exactly what I mentioned. If you just give cytokine or other kind of immune boosting reagent, then of course, now we increase the bar, and then we start to attack very small the tumor or maybe even normal cells. Now, if we reach this much, then we should give opposite the drug and the immune suppressant drugs. If not, it could be quite dangerous. PD-1's activation is once it is activated, it's kind of a switch off function. That's why cancer cell does not use it, then PD-1 system is kind of a turn on status. Okay, PD-1 is a checkpoint. I don't want to attack the outside of the cells. That's why PD-1 is blocked by PD-L1. That's activated status. But that activated status is for the cytotoxic T cells. That's kind of a switching off signal. That's why if this is not used by cancer cell, then the whole T cell function is activated. So negative over negative is kind of activating. Okay. Here, one inhibit is for the molecular level, and the other activating is that this is kind of a whole cell the activation. Tumor cell can do different strategies. It can kill the T cell, or it can just block those activity. Different ways the tumor cell can attack. Now we came back to the CAR T cells. So previous example, the question for the CAR T was, if the CAR T was made, then those the cytotoxic part is the same as of a normal T cell or not. Or in this case, if CAR T is made, then other T cells recognize this CAR T as a normal T cells. Well, T and CAR T, they are in the same side, and they may not recognize each other much. But this CAR T or T cells, they're recognized by its partners, the tumor cells. So then let's look at the CAR T again. CAR T is a chimeric antigen receptor T cells. So if the CAR T is exchanged, so depending on those the CAR T, how you made those CAR T, so that may have different other functions. If you change only for the receptor part, then downstream of a toxicity part should be same. But if you change different part, let's just say this is the original T cells, and here this is the T cell receptor, let's just say. Now T cell receptor, if they need to work, then it should have its partner over MHC. And sometimes the T cell receptor is not specific enough or good enough to recognize those antigen of the cancer cell. That's why sometimes we change those T cell receptor with this antibody-like cells, antibody-like motif, like single chain FB. Then advantage of this is you can introduce this part onto the same sequence here. Then this one, single chain FB, they do not require to have an MHC on the other side, right? Antibody does not require MHC. That's why binding affinity or selectivity can be enhanced because it has the original T cell receptor and extra recognition part here. So this is the first generation of RT. Now downstream is the same. If downstream is the same, then their cytotoxicity should be same function as the original T cells. It was a granzyme and also perforin, the function. Now, next generation, even we can add more signal here. If it is binding to something, it's second generation. Now, this one can activate proliferation of those T cells by adding this kind of stimulating signal motif here, or generating cytokine, or adding further to make these cells survive better. So by adding more and more function, so this SCFB, single chain FB, act as kind of receptors, and then this binding to the cancer cells, and then it can activate the different pathways together. Then those cells can be stronger and stronger, and also more proliferating, better surviving. So this is kind of the advancing further and further of different the generation of the CAR-Ts. Okay, so depending on those modifications, whether you change only this part or you change by introducing different functions here, then you can add up more functions further and further. Okay, depending on this, you can tell whether the functions of this CAR-T is further improved from original T cells. Yep, this is explaining those part. So not only those binding part, if the only binding, then it helps to recognize the tumor. The further function should be same. But in this case, if you add more signaling the pathways downstream, then you can activate the further. Well, if this CAR-T is a first generation CAR-T, then tumors function, let's say if they wanted to use a PD-L1, what do you think? It should work or not? If this is the first generation of a CAR-T, only T-cell receptor is changed with a single chain FB. The recognition is there, and that CAR-T should have a PD-1 too. If a tumor cell expresses PD-L1, what do you think? It may also work. It will block the function of T cells. So in the case, maybe other functions by adding, proliferating, or cytokine generation, different strategies may help further and further. CD19 is just only one example of those the potential the antigen. Actually, CD19 is a normal protein. Just the target, the cancer cell has overexpressed CD19. That's why it can be recognized. Of course, if there is any different the antigen we discover, then same strategy can be used. So again here, you don't need to have this MHC. If you can define over any specific protein of cancer, that kind of a specific protein of the cancer, what we call? If there is any specific, the protein only expressed in cancer cells, what do you call? They are called as a biomarker. Okay, so they can be, if it's a cancer, then they can be cancer biomarker. So this kind of a new biomarker or specific biomarker is always important. CD19 was just the first choice of those biomarker. If it is not perfect, then we can find different kind of more specific biomarkers. Okay. Yeah, this kind of approach may be also possible. Okay, we covered the most of the materials for today. There are many new things, so I tried to deliver this extra information to you. It seems like you guys have studied quite well for this week. So let's see. So next class will be on Thursday, and I gave you the assignment for this week. So assignment due is by tomorrow morning. So don't be late, and I will select a couple of them to present on Thursday. Okay. Any question for today's lecture or about the assignment? Any of you have chosen the phase display for this week assignment?
Can you say one more again?
Phase display.
Phage
I'll recover that.
Okay. Good. Young, do you plan to do that too?
Yeah.
Do you plan to take the phage display? If you didn't think so far, then that's okay. So this week the assignment as I gave you is any kind of, so far we have learned 3 different generations of anti-cancer drugs. The first one was the regular fast cell growing inhibitor. Second one was targeted cancer therapy, targeting those signaling molecules of cancers. Third generation was activating the immune system or changing those checkpoint of the immune system. And here the vaccination is the part of the two. So anyway, this third generation strategy is rather than attacking cancer directly, we activate the immune system. Seems like this is best way so far. The effect and also those side effects seems like this is the best way, but this is kind of a beginning of the new the approach for now. It has been only a couple of years, not a long history we have. So you can choose any kind of drugs. It can be antibody drugs or cell therapy like a CAR T, or even vaccination if it is the insightful to learn about the specific the vaccine for cancer. So any kind of those, the third generation anti-cancer drugs is the topic of assignment of this week. Any question for assignment or any topic that we have studied today?
Professor, on the post-X, there is no space for I choose some subject. There is only for the space for assignment.
Upload, right?
Yeah.
So this week I didn't give you, so I allowed you if there's any overlap, still fine. You can choose your own. So you don't need to choose and show, just you choose one the project and then show off by yourself. It can be chemical, it can be biological, or it can be cell therapy. Any of them is fine. Okay, then let's finish today's lecture here. Okay, see you on Thursday, guys.